Hello, I'm Mrs. J, and today we're going to talk about section 5.1 exponential growth and 5.2 exponential decay. The equations look the same, and really the only difference, both of them have c greater than 0. That's the starting amount or the initial value, also called the y-intercept or the vertical intercept. But the a value is what makes it grow or decrease or decay. When a is greater than 1, it grows. When a is between 0 and 1, it's a decay. Let's look at a few. Oh, c is the initial amount. So if we want to find the initial amount looking at this equation, comparing it to this, c would be your 100. The growth factor is the number that has the exponent on it. So 6 to the x. 6 is our growth factor. And since 6 is greater than 1, it is a growth. I guess this should say growth or decay. This one, our initial amount is the 210 because the 1.2 has the exponent on it, so it's the growth or the decay. Since again this one is greater than 1, it is a growth. This one, initial value again is the 210. The decimal 23 hundredths is the growth or decay factor. In this case, this is between 1 and 0, so it's a decay. And each exponential? If yes, is it a growth or a decay? And what's the initial value? So if we look at the first one, notice the variable is in the exponent. So this is exponential. 100 is the initial value. 1/3 is the growth or decay factor. In this case, since it's less than 1, this is a decay. This one, notice the variable is not in the exponent. This is x squared. It's actually a parabola that moves down 1. So this would look like this. So it is not exponential. Next one, the x's in the exponent. This is exponential. 32 is the starting amount, and 5/3 is the growth or decay factor. In this case, 5/3 is greater than 1, so it is a growth. Okay, this one, the x is also in the exponent, so it's exponential. It looks like a growth, but notice that's a negative. We could rewrite the negative part of it and move it as 1/2 to the x. So if this is negative, move your number around to make it positive. So what I did was I took 2 to the -1 to the x, because these get multiplied. An exponent to an exponent is multiplied. And then 2 to the -1 is 1/2 to the x. So this is actually a decay. This one's just a straight line, mx plus b. This one is exponential because the x is in the exponent. This is the initial amount or the vertical asymptote intercept. Five is the factor, and it's greater than 1, so it's a growth factor. Let's try a problem. In the United States during the first decade of the 2000s, live births to unwed mothers, B of T, grew according to the model below, where T is the number of years after 2000. And so that's our formula. What does the model give as the number of live births of unwed moms in 2000? Well, this is starting with 2000, so we'd be plugging a 0 in. Anything to the 0 power is 1. So this is 1.307. Now times 10 to the 6th is going to move us 1, 2, 3, 4, 5, 6. So there was 1,307,000 births in 2000 to unwed moms. The growth factor is the part that has the variable on it. And so the growth factor is 1.033. What does the model predict in 2010 and 2020? Well, I'm going to plug it in. 1.307 times 10 to the 6th .033 to the okay. So when I plug this in, I used 10 for my variable because it was years after 2000. Because at the beginning I put a 0, so now this is 10 years later, so I put a 10. So in 2010, 180833 rounding 5. 1,808,335 babies. For 2020, we would just bring that back up, change our 10 to a 20. That's going to round the 9 up, so it'll be 70. $2.5 million. So that gives the live births to unwed mothers in each of those years. But remember, when you're talking about so many years after a value, you subtract it. So we took out the 2000 and only plugged in 10 and 20. Okay. A 2.5 gram sample of strontium-90 was formed in a 1960 atomic bomb explosion. The half-life is 28 years. In what year will there be 0.625 grams remaining? Well, first let's find the equation. Starting amount 2.5. We want the half-life formula, so we go with half. And it says it goes in half every 28 years. So if we just use T here, T would be every 28 years, or 28 intervals. So every 28 it would go in half. So if I said, what was it in 14 years, 14 would be half, so you would put in half, which gets a little confusing. So instead of saying intervals, we can take and put t over 28. That way then, however many years, the 28 will be taking into account. Now in this one, t would be years. So whatever your interval would be, if you divide by it, then it will take it into years rather than into your interval. We wanted to see how long it would take to get to 625. I'm going to use, well, this one. So if we have 2.5 and we take 28 years, in 28 years that's going to go in half, which is 1.25. If we go another 28 years, it's going to go in half again, which is 0.625. 28 and 28. It will take 56 years. You can set it equal to and solve it, but we learned that in another chapter. So for right now, we would have to just keep breaking it down or plug in values until you find the right one. But okay. I wanted to look at two from the book, page 271, number 14. This graph. So we're using this graph and they're asking us some questions, but the questions are over here. What is the initial population of fish? So this is a new species of fish introduced into a pond. The size of the fish population can be modeled by the accompanying graph and P of t, where t is time in months. So this is months. What is the initial population? Initial is at time 0, so it's 10. And the size of, okay, I was just looking for units, but it's just 10 fish. So we're starting with 10 fish. How long did it take for the initial population to double? So if we started with 10, doubling would be 20. Took 5 months to double. What was the maximum sustainable fish population of the pond? Well, sustainable is when it comes to a parallel area where it's balanced. Notice here it stays about the same. What is the maximum sustainable fish population? Well, 80. Because it's staying pretty uniform at 80. So the maximum capacity or growth factor would stop at 80. The pond will keep about 80 fish once it gets to that. Estimate the number of months it took for the fish to reach the sustainable size. Well, looks like about here, a little over 30 months. It's almost there. So 30 to 35 months to hit that sustainable. This one's close, this one's right on it. $277, number 12. 12. From the graph below, estimate the half-life for the population P. Then create an exponential function to model the population T in time years. So they want it by years. So first we look at the initial amount. Now be careful, they put 0 over, they didn't put it right on the line. So at 0, we're at 40. So our initial amount is 40. And then we need our growth factor. Oh, we said half. We're using half. So when does it get cut in half? Well, if it's at 40, 20 is here. So see your initial amount, and then if you want half-life, go half of it, which is 20. So it'd be here, it takes 3 years. So it's T divided by 3. That way it'll be every 3 years. So when T is 3, 3 over 3 is 1, it will be half. And that would be your equation. So you start with your initial amount, see when it goes in half, so that's why we're using a half, and then it's T over that value. And that's everything in 5.1 and 5.2.